Good morning, good afternoon, and welcome to our panel discussion, the McKim Creed ongoing series on energy storage. Today's topic is bridging the technical and financial gap of energy storage. I'm Saul Haroon, your moderator and director of renewables rather, and adjunct at Georgia Tech. And I'm joined by two of my friends and professional colleagues, Ivan Reguera at Power Energy and Joel Viduna at Strata Clean Energy, two power hitters in the energy storage field. So I know we're going to have a really fun conversation and educational as well on energy storage. So our discussion today, allow me to share my screen here a little bit, will focus on energy storage, the technical nature, but particularly the financial metrics of energy storage. And we'll look at the evolution of financial storage, financial metrics, I should say, the evolution of energy storage itself, some of the use cases. What tools do we have right now? How have they kept pace? What's the latest in system architecture? How have these standards evolved? And what should we watch out for in systems integration? And wrapping up with some final thoughts by Ivan and Joel. A little background on McKim Creed. We're a full turnkey engineering firm, people helping people, providing all manner of engineering services from structural, surveying, civil, electrical, mechanical, and so on, in various spheres, many energy storage and renewable energy, of course, being one of them too. So passing it over to Ivan. Ivan, please introduce yourself.
Yeah, thanks, Saul. Hey, good morning, everyone, or good afternoon. So I am Ivan Reguera. I'm the Southeast Sales Manager for Powen. I've been with the company since March of 2021. And prior to this, to Powen, I spent 17 years in the EPC space, building plants of all kinds, coal, nuclear, combined cycle, solar, and now energy storage, of course. But just to give you a little overview of what Powen is today, we're probably one of the least known energy storage integrators, but probably making an outsized impact on the industry. So we have over 430 employees, 210 in the US, and a couple hundred in China and Taiwan. We have over 1.2 million hours of runtime on our systems. We have over 5.5 gigawatt hours installed or under construction. And we like to boast that we have greater than 98% average fleet-wide uptime availability. And so we've done a lot of work over the last 12 months to gather all this performance data and really understand how our systems are performing. So really proud of that. Here is just a little example, a few examples of some systems we've recently installed. So a couple of these systems are for Southern Power Company. Recently announced the commissioning of the Garland and Tranquility sites. And so this was a really groundbreaking achievement for us. It was the largest system commissioned to date of 352 megawatt hours combined on these two sites. So that's Powen in a nutshell.
Thank you, Ivan. Joel, over to you.
Hey, good morning, good afternoon. My name is Joel Viduna. I'm the Vice President of Energy Storage at Strata Clean Energy. A little bit about me and then a little bit about Strata. I'm an engineer by training, went through a power generation and construction-focused curriculum, although I've never really worked as a real engineer. After I graduated, spent 10 years working for Kiewit in a background similar to Ivan, building largely fossil fuel power generation stations around the United States and Canada. Also dabbled in some other stuff like liquefied natural gas and ethanol. After 10 years of that, I went over, spent 7 years at a consultancy called Luminate, where we did technical, commercial, and environmental due diligence, supporting mergers and acquisitions, project finance, bankruptcies, restructurings, things like that. Got to work on a variety of different energy technologies while there. I was originally kind of hired as a fossil fuel expert. And then in 2015, I started their energy storage practice in the really early days. And that practice grew and grew, and before we knew it, we had reviewed and worked on over 250 energy storage projects, which was a lot of fun. In the last year and a half, I've been at Strata Clean Energy, where I have overall responsibility for the BESS business. Spend most of my time focused on utility scale energy storage development, but also play a key role in our EPC, O&M, financing and asset management groups as well. As for Strata, Strata was actually founded in 2008 as a residential thermal solar installer in North Carolina. Over those last few years, it's developed into a pretty large vertically integrated clean energy platform with development, EPC, O&M, and an IPP group. We've installed over 2.5 gigawatts of capacity across 250 projects. And we have 4 BESS projects that we've developed or built that are operating. We have 6 under construction, and we have 60 projects, BESS projects in development comprising about 25 gigawatt hours in about half of the United States. So quite a few irons in the fire. And then in the theme of what we're talking about today, which is a lot of financial impact, aspects of energy storage, we are very active in debt and tax equity markets to enable our solar and BESS projects. So that's a little bit about Strata.
Thanks, Joel. Thanks, Ivan. Now that we've introduced ourselves, you as the audience, please feel free to type in your name, where you're from, and anything else you'd like to share, particularly your interest in this conversation. A few housekeeping things. We'll take questions at the end. We'll run for around 45 minutes or so to 12:45, 12:50 Eastern time. Probably we'll run a little bit over for generally you have very spirited questions to around 1:15 or so. So feel free to type in questions as they occur to you in the chat box. Ivan, we've seen a lot of things happen in energy storage in the last 5 years. Certainly, the economic landscape has changed. Energy storage has become more economically viable. We've seen situations in California, in Texas, in the Northeast. I think we've also come to better understand some of the use cases for energy storage, especially on the heels of other renewables such as PV and wind and so on. Can you speak to a little bit more about some of these use cases as well as what you've seen changing in the economic viability of energy storage?
Yeah, and Joel and I have talked about this before, but I feel like we're quickly seeing what is kind of a transformation of the use cases for energy storage systems. And so what you're seeing on the screen is sort of a summary of all the energy storage services that can be provided by a storage system. And I think earlier on in a couple of years ago in the energy storage field, we were seeing a lot of frequency regulation, a lot of voltage control, a lot of what do they call what am I looking for? Power smoothing or power firming capability. So I think what we're moving to, the industry is certainly moving toward more of our energy arbitrage market, right? So as long duration storage becomes more financially viable, especially with the passage of IRA and all those tax credits that come with it, standalone storage specifically now, I think what we're seeing is that we want an energy storage system, and customers are looking for energy storage systems that can do multiple services, right? That are kind of a Swiss Army knife that can do all these things. And so that's kind of the biggest theme I've seen over the last couple of years since I've been at Powin, that shift toward ancillary services to more energy shifting and long duration storage.
Well, thank you for that. And Joel, I know you've got a few comments on this too. So if you could further elaborate on that from your perspective, what you're seeing, that'd be great.
Yeah, I agree with Ivan. For a grid connected BESS, whether it's at distributed or utility scale, usually it's ancillary services that open up first in a market. So that's either spinning reserve or frequently regulation up and regulation down. And then as more and more intermittent renewable energy gets on a grid, and particularly when more solar gets on a grid, and as more batteries get deployed, what you see is that the ancillary services tend to be a pretty thin market, and batteries solve those issues pretty quickly, and the price signals will drop resultant of that. So it doesn't mean the batteries aren't still there helping maintain 60 hertz on the grid. They are, but the value drops away as more people chase that opportunity. And then you see that you get more of a duck curve type effect in the market as particularly solar penetrates deeper. And then you can use a battery to bulk shift energy from the middle of the day to the early evening when it's needed. So I fully agree with what Ivan has said there. Regarding the broader economic landscape, my answer in this is mostly focused on grid connected systems, both distributed and utility scale. So you should view my answer through that lens. But on the capex side, we've seen lithium ion systems decline. roughly 7% year over year in recent history, up until last year when costs abruptly went up for a variety of reasons. But the industry is still full speed ahead. And now that we have the Inflation Reduction Act and the associated standalone energy storage tax credits, that's kind of offsetting some of the capex increases that the industry absorbed last year.
Mhm.
On the policy front, we've had several FERC orders in recent years that have enabled the participation of BESS in both regulated and deregulated markets. And so that's why, my company has assets in over half the United States right now, with viable ways to make money off those assets and to solve technical problems on the grid. And in many markets, we have out-of-market incentives that help batteries pencil out. So this could be things like the Massachusetts Clean Peak program, or various incentives in Illinois and New York that help incentivize people to deploy batteries. And then, going back to the idea of bulk shifting of energy, some interesting things have happened. As we've had the proliferation of zero marginal cost solar on the grid that isn't always produced at the time of day when you need it, that provides a cheap, free, and sometimes negatively priced source of charging energy for our batteries. And, even before the price of natural gas went up due to the Russo-Ukrainian war, proliferation of LNG and things like that, we could already make money and solve a technical problem on the grid by buying cheap energy from solar predominantly in the middle of the day and discharging it later. As of this morning, though, natural gas is $10 per MMBTU. And if you think about the efficiency of a natural gas plant, the best gas plants out there are, 10,000 heat rate. What that means is that the minimum price that a gas plant can sell energy at and break even is $100 per megawatt hour. So if we're charging from, sub $30 per megawatt hour energy, and we're discharging $100 per megawatt hour energy, despite round trip efficiency losses, there's a pretty clear use case there. And so, that's kind of from a macro level how I view the change in the economic landscape over time and how it leads into today's use cases.
Yeah, you bring up a great point, Joel. I mean, I just want to touch on that. I mean, I've seen such a dramatic interest from the natural gas industry and energy companies that are traditionally natural gas focused. And they certainly recognize the volatile nature of natural gas and the fact that, hey, I mean, energy storage can provide them so many benefits, especially when they're part of managing the grid or providing, firm capacity to the grid. So absolutely, couldn't agree more on that. And also, you brought up the point about the use cases being so different over time, and I think that provides or brings so much complexity for a customer modeling a project. And I think that's why it's so important that a technology solution be able to do one thing the first few years of its life, and then also do a second thing in its later half of life. So, anyways, just some things to think about.
That's a good point. Saul, do you have the slide that we discussed yesterday that shows the CAISO best fleet dispatch pattern on the same day in 2020 and 2022? I think that will really help illustrate Ivan's point there. So on this slide, what you can see is that if you go to CAISO's website, you can see on any day in recent history what the entire best fleet within CAISO was doing. And what I thought would be interesting is to pull up the same day in August 2 years ago and the same day August this year. And I just picked a random day. And what you can see is 2 years ago, when the best fleet looks like it was, 250 megawatts or less, it's kind of just randomly fluttering around doing frequency regulation, maybe a little bit of real-time energy arbitrage to balance supply and demand. Fast forward 2 years on the same day, when we have 2,500 megawatts of batteries operating on this particular day. And what you see is that batteries are solving the duck curve. We're discharging during the morning peak. And then as sun comes up and solar starts generating in CAISO, we are charging during those 5 hours or 6 hours in the middle of the day when solar is plentifully available and is causing locational marginal prices on the grid to be quite low, so economic for charging. And then what you're seeing is when the sun goes down but load goes up, the infamous neck of the duck curve and the head of the duck curve, batteries are discharging for the next 4 or 5 hours, and they're helping flatten out the duck curve in a very economic fashion in California. And so I've always found that this is like a really interesting glimpse into the future for most markets, because California has always led on solar deployment. And, we're seeing massive solar build-outs in MISO, PJM, and elsewhere in the grid. And I suspect that you'll see more and more of a duck curve develop in those markets over time. They aren't going to have the same shape as CAISO. Some markets have more wind that distorts that shape and things like that. But the point is that 2 years ago, batteries were doing frequency regulation, and that's where the majority of the money came from, and that was the technical use case. And now we're bulk shifting energy from one time of the day to another.
Yeah, I want to add to this, Joel, because I think this is a perfect example of what we're talking about. And this speaks to the conversation I've been having with so many customers lately. They keep asking me to quantify in certain markets how many cycles per day would be required to satisfy frequency regulation, and then also capacity, firm capacity discharges as well. And it's like, well, that's a moving target, as you see here. I mean, it's dynamic, right? And so it's something we struggle with considerably, and I know our customers do. But we always price and model systems based on cycles per year discharged, and charged and discharged being one cycle. So obviously that's how customers are modeling. We're modeling the sizing and degradation of a system. So this is a struggle, but this is a great example of what most markets are going to do, right?
I'd really like to get into the tools and modeling aspect, but before we do so, just to really understand what you guys are saying, that it's become very clear what those use cases are for the utility scale, for large scale distributed systems, and utilities have a much better understanding, and the deployment is clearly there, the economic case is there. What about on the CNI space? If you could talk a little bit about that, because particularly what I'm seeing is there's still this notion, and perhaps to some extent rightfully so, that batteries are expensive, batteries are not viable. PV is definitely a home run, or can be a home run more or less now, but batteries maybe not. So can you speak to a little bit about the use cases and the economic viability in the CNI space?
Yeah,
and I
ahead,
think
Yeah, I can go first. I mean, when I think of CNI, I think of it kind of in terms of corporate off-takers, and then also customer-sided distributed scale energy storage. The customer-sided energy storage business has been around for a while. Pioneers like Green Charge, AMS, STEM, established clear use cases for that, primarily in offsetting tariff demand charges for that their utility imposed upon them, and then occasionally energy arbitrage. But generally speaking, if you were on a time of use tariff, as cheap energy was not enough to offset rent trip efficiency losses, and so there was a lot of excitement about that early on. I think now that's let's call it like a mature business, but people aren't as excited about as they used to be. And so that's just a matter of math and financial engineering. So there are still companies out there that can give you no money down batteries to site at your business that based off of your tariff will reduce your demand charge using AI, machine learning, whatever buzzword you would like to use to describe the algorithm. So that still exists out there. As far as corporate offtake, there's all sorts of zero emissions pledges or 100% renewable energy pledges. By and large, I think right now what that means is for a lot of customers, rec purchases, which are not time matched, and for others, it's additionality, but still not time matched. Virtual PPAs, things like that. But for folks like Google and others that have made time matched commitments, I do believe that they will continue to be interested in energy storage, and when the time is right, they'll pull the trigger. But I don't see a massive market for that because it's not necessarily a clear business case. So unless you have like a very ESG focused business that has money to burn, they're probably not going to voluntarily sign offtake agreements for batteries when they're not yet getting that deep ESG pressure to have time matched renewable energy.
Yeah. So my perspective on that, and I think you're right. I think the focus for CNI becomes customers who are in the commodity or low margin industries. And so energy might make up a larger portion of their cost of goods. So for instance, I used to work in the plastics industry for a couple of years. I managed energy for this particular company. And many times energy was the largest single expense aside from the facility lease itself. And so just participating in a couple of demand response events per year could mean that we would basically offset our entire year's electricity usage, which was nuts, right? But that's the way it is in some markets. The benefit, or I think the opportunity in the CNI market, is still this opportunity for peak shaving, right? Where For instance, I'm working with a natural gas transportation company, and they are looking at energy storage units of 2-hour duration behind the meter, moving natural gas through their pipelines, right? Because they're getting hit hard by these peak demand charges. And so in certain markets, obviously, that can be considerable. I think there's a great table with a double column showing the difference between the time of use rates and the peak demand rates or something to that effect. But I think that's a great example of showing what the savings could be for a small storage system behind the meter for any given commodity company.
I think
Sorry,
you're muted, Saul. There you
yes,
are.
I do. Yeah, I finally figured that out. So that really helps us understand this. In terms of looking at financial metrics to weigh the cost effectiveness of an energy storage solution, there's an alphabet soup that you can look at: MPV, IRR, payback, all that, these various metrics. And what I found, some clients, some customers would just simply look at the simple payback and say, oh, this works or it doesn't work. Can you speak to a little bit about some of these other metrics and why you think they may or may not be useful, such as NPV, IRR, or whatever, ROI, etc.?
Yeah. This is like something I'm pretty passionate about. Just because I think a lot of energy storage participants are specialists, and the industry needs specialists. But this is an industry that rewards understanding the big picture. And so to me, there's many variables in the analysis when I'm thinking about what comprises an energy storage project. We've got available land size and the marginal cost of buying more land. You have fixed interconnection variables, capex, opex, tax credits and availability of tax equity, energy density, available offtake, permitting requirements, and available incentives. And so if you're really going to assess the economic benefits of an energy storage system, you got to have technical, commercial, financial, and policy chops and really think about how that multivariate equation comes together. Because if you do a purely technical analysis or a purely financial analysis, you're likely to get subpar results. And a perfect example of this is there's like no quicker way to trigger my team than if I'm taking a sales meeting with a long duration energy storage company and the first slide is levelized cost of storage versus lithium ion, right? Because it fundamentally mischaracterizes how batteries are valuable to the grid and what I really need. So what I can tell you is like when I model out whether I need a 4-hour battery or a 12-hour battery, right now it's really hard to make money with a 12-hour battery, if not impossible in most places. But for various reasons, I can make money with a 4-hour battery. That doesn't mean that won't be the case in the future, but I'm deploying projects now. Similarly, I don't need 30,000 cycles. I need that like I need a hole in the head. I have like a 20-year asset life. Maybe I could do longer, but 20 years is kind of a magical number for a variety of reasons, especially in the lithium ion world. And 1 cycle per day is not necessarily a technical limit, but it's a convenient limit. Because if you look at the cycle life of batteries, the calendar life of batteries, how long off-takers want to sign contracts for, something that gives me 1 cycle per day for 20 years, which is something over like 7,000 cycles, is what I'm looking for. I don't need 30,000. And so if you're going to take a long duration storage technology with high capex, amortize that over 30,000 cycles and tell me you're more competitive than lithium ion, that is not true. So that's why I say that a purely technical or a purely financial analysis is not what's ideal. So what Strata does and what I think a lot of people do is we have a techno-economic model or a variety of tools that form a techno-economic model. For each individual project, we input what's known. Maybe interconnection is fixed, maybe it's not. Maybe land size is fixed, maybe it's not. Maybe my equipment choices are fixed, maybe they're not. So we input those knowns and then we solve for the unknowns, optimizing for the highest possible levered rate of return. And I think that in a capitalist society, like it or not, that is the way that business works, and that is the way to optimize an ideal energy storage asset.
Yeah, I agree. I think there are other metrics other than financial to look at. Let's just talk about natural gas, right? It's at $10 per million BTU. If I'm a natural gas intensive utility, I'm looking at energy storage as a blanket to protect me from things like that. I can't overestimate the impact and significance of the cost of natural gas on the utility industry in general. I mean, I think it dictates so much of what they do going forward. And I know that based on the discussions I've had over the past several weeks with utilities, even hosting them in Portland, Oregon at our battery lab. I mean, the interest is real and significant.
Yeah, I mean, like without a doubt, Power Markets 101, and any Power Markets professional in this call would agree with me. Most wholesale power markets, so not the regulated side, but the deregulated markets, CAISO, ERCOT, things like that, the marginal generator is what sets the price of energy at that point in time. And at most times of day, in most markets, natural gas plants are what are the marginal generator. And the math is very simple: the price of natural gas, your heat rate, and the minimum price that you can sell electricity for to be profitable. And so, even with gas as expensive as it is, that is essentially who the competition for energy storage is, particularly peaking plants, not combined cycle plants, but peaking plants is who we're competing against. Wood Mackenzie, formerly Green Tech Media, did a study years ago. I think it was like 2018, and I think it's still relevant today, where they analyzed the entire United States peaking fleet, and they looked at what the average duration of a dispatch was. And I think what they found is that something like north of 80% of dispatches were less than 4 hours in duration. So when you think of what makes batteries economic, it's competing against natural gas peaking plants, where they have a minimum price they can sell at to be profitable, but they have a fuel cost. When I'm a 4-hour battery, my fuel is either free or very cheap, certainly cheaper than the cost of natural gas, and I'm selling at whatever the marginal price is, which is set by the gas generators that are still in the market. And that's why it's such a good economic use case and a good technical use case, regardless of how you might feel about social justice or environmental benefits associated with a battery. It's just good business.
Yeah, I think the other point to remember that I always like to point out is that I saw a metric once that showed that the top 10% of peaking energy produced costs on average 25% of their overall operating costs. So
Yep.
they have huge incentive to reduce that peaking cost of power.
So you guys mentioned something about the tools and modeling some of this stuff. As we know, in the PV world, there's been a lot of evolution that PV says, some of the European tools, Helioscope, and even tools like Homer Microgrid and so on, have come a long ways in helping us model energy generation. But what about energy storage? What have you seen happen with these tools, and how we can effectively model energy storage, particularly the financial aspects of that, whether it's in the CNI space or in the utility space? What sort of evolution have you seen there? And are there tools that you're familiar with that our audience can even engage in, perhaps engage with?
Yeah, it's interesting. When I started the energy storage practice at my prior company, we were doing a tremendous amount of solar work. And in the solar world, if you are looking to use other people's money to build your solar project, you have to use PVsyst. PVsyst is far from the easiest tool to use, and its competitors, Helioscope, Aurora, or whatever, are quite good. But if you want to get somebody else's money, you have to use PVsyst, right? And so for a long time, I went on this hunt, in hindsight, a frivolous hunt for the PVsyst of energy storage. And we tried out the early versions of the SAM model at NREL, Energy Toolbase, Homer. And like all those tools are good for something, and it can help you look at very individual situations. But ultimately, what I came to the conclusion of is that the US power grid and how we trade energy in regulated and deregulated markets, where everybody's got different rules, is the most complex in the world. They all have different constructs to trade energy and different incentives. And so what I came to the conclusion of is that at a certain point, if you're operating in a lot of different markets, utility scale, CNI, DG, regulated, deregulated markets, you always end up back in Excel or some code-based solution like Python, MATLAB, or R. And there's really no getting around it if you actually want to develop a precise model. So the off-the-shelf software programs are really good, particularly for behind-the-meter CNI stuff. I think the Energy Toolbase and others can be pretty robust at that. But for utility scale, where I'm doing different things in Georgia and different things in Colorado and different things in California and Texas, they just aren't a good fit for it, in my opinion. And so that's why you always end up back in good old Excel or a code-based solution.
And Ivan, I think you've run through some of this as well. At least some of your clients have,
Well,
perhaps.
I will say that the conversations that I've actually had with Joel about this, the question always becomes, what is the technology going to look like a few years from now, right? What is the energy density of the cells we use going to
Yeah.
be? I think this is a common conversation that we've been having, and so I'm not a user of these applications, but my question would be, I wonder how well they handle the modeling of different energy densities over time, and so that's an interesting question for me.
Yeah, that's a very good point. I'm sharing on the screen for the benefit of our audience some publicly available through the DOE tools like REOpt, mentioned System Advisor model, Homer, also which for microgrid modeling came out of the DOE NREL program as well. So here are a few tools that customers can use, but energy tool base for behind the meter and so on, a private industry tool. But to your point, what I'm hearing you guys say is that there has been definitely a fair amount of development and evolution in these tools, but the effectiveness of that really depends on the use case, and it depends on whether it's behind the meter or in front of the meter, but also looking at what's going to happen 5 or 10 or 15 years from now. And that's the challenge that we're having. PV is pretty straightforward. It's well understood. Energy storage, electrochemical devices, whether they're lithium or flow-based batteries or whatever, it's much harder to characterize those. And it really depends how you're going to use them, particularly not just today, not even 1 year from now, but even 5 and 10 years from now. And also taking into account the degradation of those batteries. Is that what kind of I'm hearing from you guys a little bit?
Yeah, and Saul, I actually will give a shout out. I'm looking at the comments right now. So, friend of mine, Corey, who's been with Fractal for a couple months now, in a sales position. Fractal actually has what they call the Fractal model, and it's kind of the best of both worlds. It has a very robust code back end, and it has a familiar Excel front end. And I think of all the off-the-shelf tools that are out there, it does the best job of kind of combining the technical and the financial aspects. And it also optimizes for IRR, which is what we're looking for. And it's particularly good if you're trying to answer questions like, I have a fixed land size and I have a fixed interconnection and a solar and storage project. How much of that should be solar? How much of it should be storage? Should be AC coupled, DC coupled? That tool is really good for that. So I didn't mention it by name, but Corey's being a good salesperson right now, and I will give a plug that the Fractal model is quite good.
That's fantastic. So moving on to kind of like system architecture, I know there's so much we could just talk about from the tool-based side of things and the financial metrics and so on, IRR that you just mentioned. But moving on to system architecture, you mentioned something interesting, DC coupled and AC coupled, whether it's behind the meter or in front of the meter. Could you talk a little bit more about that? Could you guys talk a little bit more about that? And also in general about the system architecture evolution?
Yeah. I mean, a couple seconds on that. I mean, in the past, prior to IRA, the Inflation Reduction Act, we've seen a lot of interest in DC coupled systems, and I think Powen's been a leader in that regard. I think going forward, the IRA has really presented the opportunity for standalone, storage systems to be the mainstream, right? And so I think that's going to lend itself, obviously, to AC coupled solar systems as well. So I just think that's the most immediate impact. Yeah, so I'm interested to see how the DC converter market evolves after the IRA.
Yeah, I mean, from my perspective, it's really interesting. I think engineers love efficiency and they hate the idea of wasting energy. It's just like programmed into us, right? And so I think at first glance, a lot of people with technical backgrounds will gravitate towards DC coupling of solar and storage under the idea that wasting electrons is sacrilege. But I think once you consider the broader supplier landscape of available AC coupled equipment or DC coupled equipment, you consider the complexities of project execution, where you might be able to scope an AC coupled system out to separate parties, but it's a little harder to do that for DC coupled systems. You think about the complexities of augmentation. You think about some FERC orders in recent history that have made it not as big of a deal to have redundant solar and storage inverter capacity that allows you to software limit your output to stay below an interconnection capacity. And you think about some of the operational limits of DC coupled systems, where in the real world, bidirectional power flows are not as easy from the grid as you might be led to believe. I think AC coupled systems are often the better choice. One exception that I would say is, if you have a fixed size interconnection and a boatload of land, and you have an off-taker that really values the production of energy over flexible capacity, in that case, it makes sense to oversize your DC array, recapture that energy that would otherwise be clipped with a DC coupled system, and discharge it later. But if you have an off-taker or a use case that requires bidirectional power flows from the grid and very flexible operation, I think AC coupled tends to be the better choice most often.
Just for the benefit of the audience, those who may not understand DC or AC coupled quite as well, the notion of DC coupled, as I understand it, is that the PV, that all the DER resources, the PV and energy storage, share the same DC backbone, with the notion that a lot of renewable sources are direct current DC. So why convert to AC and then back to DC? And thus you can garner a little bit more, somewhat more efficiency by connecting all the DC resources, the battery, the PV, etc., on the DC side of things. But it also means that they're tightly coupled and perhaps a little bit harder to scale. Whereas what you guys are talking about, the AC coupled, is you could have the battery and the PV coupled on the AC bus, decoupled from each other, and scale them independently of each other. Is that a fair statement about the DC?
That's right.
Versus,
yeah, okay. So like a DC coupled system will typically have lower capex, and it produces more energy at the POI in most common configurations. And so that's why most people naturally gravitate towards it. And it's only later on when you realize that perhaps maximizing the amount of energy you produce may not be what a lot of off-takers are looking for, or you look at the idea of man, there's only 2 or 3 DC coupled solution providers on the market, but there's a gazillion AC coupled ones. And you start to think about, man, will those DC coupled guys be in business in 10 years when I need to augment, or, if I need them to fix it, versus on the AC coupled side, it's like, okay, this inverter guy goes out of business, I can swap it out for another one later on. It's not that simple, but those are where you start to come back to the idea that AC coupling might be a better solution.
Yeah, right. And just to build on that, there's also capex, installation, and opex implications of a DC coupled system. So typically, a DC coupled system, you're going to have that storage system dispersed throughout the solar array, right? So you can imagine the difference between a nice AC coupled storage block that's a nice rectangle on your layout, being now dispersed in different chunks out throughout your PV array. And just imagine the differences in installation and OPEX costs there.
Yeah, and what's really interesting, Saul, is like a buddy of mine, Ian Graham, just commented. He works for FastGrid, and Ian flies all over this nation commissioning battery projects. And he said that DC coupled is niche and AC coupled is much more flexible and robust. He's totally right. Like in the real world of deployment, very few people are actually doing DC coupled. And so it's one of those things where you kind of think about them as 50-50 choices, but they're really not. The DC coupled market is very niche. It's not super common. There's a situation where it can make sense, but more often than not, it doesn't.
Yeah, that really helps clarify. This is a slide that Joel has shared with us, and it's just a general architectural, neither DC nor AC, but kind of building on what you guys are saying in terms of where batteries reside typically, and the efficiencies or inefficiencies involved there. So where the losses are. So is it fair to say that a round trip efficiency for a typical lithium system may be anywhere from 85 to 90% or so when you account for charging, whether it's from, let's say, the grid or from renewables into the battery, and then discharging out into the grid or into the local loads? Is that
yeah, I mean, you got to be careful how you characterize round trip efficiency. And what you'll discover is that most OEMs will frame round trip efficiency in the way that is most suitable to them, right? So, frequently what you'll see is that like auxiliary loads are excluded from the equation, which may or may not matter. And then you'll discover that certain architectures are different. So if you buy a Tesla Megapack, the cooling loads are inherently baked in to the operation of the battery. You couldn't meter them separately if you wanted to, versus if you go with a power and centipede system, just the way it works, it is a separate electrical bus and it can be metered separately. So like generally speaking, like yes, 85-ish to 88%, I would say all in is where you're at beginning of life. And then over time, the internal resistance of the batteries gets worse. You've got all these different augmentation and mismatch issues that develop over time. So, figuring out what your round trip efficiency at end of life is can be a little bit complicated. But at beginning of life, all in, yeah, you're in the ballpark.
Okay, great. So Joel, you and I were talking about moving on to kind of the standards evolution. And as we know, standards are vital to moving things forward for safety purposes. Particularly, there's a notion that batteries can, have certain safety issues that we're all aware of. Can you speak a little bit about the evolution of those standards and how they're protecting customers and all of us, and what's going on in that world?
Yeah. I'm not personally in the weeds of the standards, not to the level of my engineering team that reads them. But at a high level, I think of the world in pre-McMicken and post-McMicken terms. And so for those that are not familiar, McMicken was an APS project that caught fire a couple years ago. Pretty terrible. A couple firefighters were injured, and it was pretty bad. It wasn't great. But what was interesting is before McMicken, this industry was the Wild West. We had certain codes and standards, but honestly, we were basically building the plane as we were flying it. It was like, I don't know, should we put FM 200 or Novec 1230 fire suppression? Sure, it's better than nothing. And we were figuring it out as we went because we didn't know what we didn't know. When McMicken happened, despite how terrible that incident was, I think that from a technical perspective and a life safety perspective over a long run, it really snapped the industry to attention, and it was one of the best things that ever could have happened to improve the industry as a whole. And what came out of it was a lot of best practices and really good codes and standards like NFPA 855, UL 9540, UL 9540A, International Fire Code Chapter 12. And so, certainly the people that sit on those code committees and a lot of us engineers that are in the weeds would argue that those codes are far from perfect, which is something I agree with. There are people, very smart people, working to improve them. And I think my main case is that this is a way better code and standard landscape than it was before McMicken happened. And lithium-ion energy storage systems are quite safe in a very statistically sound and provable fashion, particularly when you compare them to incident rates of the fossil fuel fleet. One of the things that when I'm testifying, say at a hearing to try and get one of our projects to get a zoning approval or something like that, I get a lot of gotcha questions or what if questions, right? Like, what about this battery fire? What about that battery fire, right? And when you actually dig into the data and do some empirical analysis, what you discover is that no matter how you slice or dice it, lithium-ion energy storage systems are as safe or safer than the alternative. Kelly Blue Book did an interesting study on EV fires versus internal combustion engine fires. I think it was last year. And I don't remember exactly what the statistic was, but EV fires were a order of magnitude, like a fraction of what internal combustion fires were on an incident rate, life safety basis, no matter how you slice or dice those numbers. And the same is true, I think, in our industry as well. The difference is that if you see an internal combustion engine fire on the side of the road, or if you hear about a coal plant fire in their coal pile, nobody gives it a second thought. It doesn't make the news because you're like, oh, that makes sense. Coal piles occasionally catch fire, and in internal combustion engines run off of gas. Gas is flammable, and mentally that's just something we take for granted. But if a Tesla's on the side of the road catching fire, the local news shows up and puts it on the nightly news, right? So that's why I think that it's really important in this industry that we be intellectually honest and we bring data, not anecdotes. Because when you dig into that data, you discover that lithium-ion energy storage systems are quite safe.
Yeah, couldn't agree more with that. I mean, safety is paramount in the industry, and we're in such an innovative industry from a product perspective. Things are changing so fast that we're taking it, all of us do, all the industry OEMs and technology providers, we go above and beyond to test our systems beyond what the standards are, beyond the UL standards. And we do fully destructive testing so we can understand how that product is going to fail, right? So, the best way to make something safe is to make it predictable, know how it's going to operate, know what its failure modes are. And if we can predictably show that this is what happens when a cell goes into thermal runaway and what's going to happen within the product if that were to occur, then we can, at least inspire some confidence that we know what the product is going to do and how to address it when it does happen. Because things always break. That's just the nature of mechanics and electrical systems. But how do we respond to them when they happen? That's the question. And how do we make it safe for all the operators?
So what you guys are saying, in addition to the evolution of the standards, NFPA, NEC, and UL, and IEEE, and all of the others, which are working hard to ensure the safety of these products and complete solutions, but also I should say the control architectures, the control systems that are monitoring this and navigating through what's going on, also have predictive elements to figure out if something is on the verge of breaking or catching fire. So it's a matter of not only just the standards, but the AI and the intelligence and the control that you're putting into play into these integrated solutions are also ensuring greater safety. Is that fair to say, Ivan?
Oh yeah, I think it's multifaceted, right? You have software technology that controls performance and safety. You have mechanical design that affects performance and safety. You have the battery cells themselves, the architecture and electrochemistry of those cells that control and determine the consequence or the result of malfunction. So I mean, there's so many ways to look at it, but at the end of the day, Joel's right. There's going to be these occurrences in the industry. The question is, how predictable were they, and how do we respond to them and make them so that it's mundane, right? So it's like when the car engine blows up on the side of the interstate. Most people don't even bother to look now. So we hope to get there eventually with all these technologies, right?
Great, right. So moving on to kind of a system integration. We've talked about batteries, but batteries could be sold individually as units, or it could be sold as part of a complete solution or complete system. And of course, Ivan, I know you are working diligently on that in that area. Could you speak to us a little bit more about the complete solutions and the importance of that, and what's your take on that versus individual batteries?
Yeah, that's a good question. I over the last couple of weeks, I had some really interesting conversations with customers who are used to buying a product at the DC level, and that's understandable. Maybe that's how they're looking to get the best dollar per kilowatt hour, and maybe that's worked for them in the past. I think what we're trying to bring to the market is to show a customer, hey, we bring you a complete turnkey system, software, hardware, integration, deployment, all those services and product under one package, and then we can stand behind that product and guarantee it. And so we're taking safety and performance to a higher level, right? So we're basically saying we can do a better job of guaranteeing performance and safety if we have the whole package, technology, software, integration, et cetera, with our hardware and all that design. And so when you break those things apart, I think inherently it becomes more disjointed, more opportunities for failure, more opportunities for performance, detriment to performance and safety. And so that's our stance. And that's kind of, I think, what sets us apart in the market. And again, our primary focus has always been on safety. And I think every other integrator as well, they have a tremendous focus on safety. And so none of us want to see these incidents occur. And so that's why we like this integrated solution the best. And we don't like to break it out separately.
Yeah. I mean, Ivan's biased, but I totally agree with him. Saul, we talked about this a little bit yesterday in prep for this session. And when I started doing this 7 years ago, there wasn't necessarily these pre-engineered, pre-manufactured, pre-packaged solutions on the market, right? And so I got to see a lot of projects executed a lot of different ways. And what I came to determine is that some people think of a BESS as a thermal power plant. Where an EPC contractor takes a GE gas turbine and a Foster Wheeler boiler and a Siemens turbine and a Holtec condenser and a GEA cooling tower, and they throw it all together in a power plant that generates electricity. They build it, and that's how it's done. And so in their mind, I should buy Samsung racks and this enclosure from this dude and some SMA inverters and some air conditioners from Carrier, throw it on the roof, put it together, and that is the way to put together a BESS, right? And you could probably put together a spreadsheet that shows that the buyout cost of all those widgets is pretty alluring. And then other people think of a BESS like, let's say, a gas turbine, right? Where you would never build a gas turbine with a GE intake, a Siemens compressor, and a Mitsubishi combustion chamber or whatever, right? Like that makes no sense because it has to be bought as an integrated, pre-engineered, pre-manufactured product. But what you're going to get is a turbine that shows up and is reliable, and you already know exactly how it's going to work, things like that. And time again, what I observed in the early days of this industry is that if you develop a bespoke BESS and throw together different stuff, engineer it together, like it is a very intellectually interesting problem, but it will take up more space because you can't possibly optimize energy density. It's likely not going to be as efficient as you would like because maybe your air conditioner sweet spot is not exactly in line with your heat production profile of the batteries. Or you're taking additional execution risk because maybe this widget and that widget and that widget don't show up at the same time, so now you've got a schedule problem. So for a variety of reasons, I'm a very firm believer that energy storage should be viewed as a mass-produced product and not a custom project. And so as such, Strata really loves these pre-engineered, pre-manufactured, proven solutions. They're deployed over and over, so they gain the benefit of iterative improvement. And I think iterative improvement is really important because you can't design your way out of all engineering problems. Like, you are going to discover issues in the field, and if you iteratively improve upon those, little by little, you're going to chip away and you're going to have a very resilient, reliable, and safe product. But if you're constantly reinventing the wheel and coming up with a new combination of widgets to form an energy storage system, it's going to be less reliable, and I think it's going to be less safe. I also believe that you will end up with shorter schedule durations. You will end up with fewer recordable incident rates and better quality by shifting these person hours from the field to the factory. So for a variety of reasons, I'm just a huge fan of these pre-engineered, pre-manufactured solutions like the Pound Centipede and others, because the opposite just doesn't tend to work super well for people in my experience.
Got it. And it's fair to say that we're seeing that also in the C&I space, complete package solutions, whether they're appliances or complete integrated solutions for the 100 kilowatt hour to 1 megawatt hour space as well.
I will say that industry is underserved, though. Back in the day, a lot of integrators, some of which are not here anymore, they had CNI, DG, and utility scale product lines, and a lot of them have discontinued that CNI product line, unfortunately. So it can be really hard to come up with a solution for a behind the meter application of CNI or DG scale. And so what I've seen is that a lot of those projects are forced to go the more custom route out of necessity.
Right. As we approach the top of the hour right now, there are several questions that have come in, and I'd like to kind of address those as well. So we have one from Corey. Do you anticipate the new storage ITC, particularly I think coupled with the new IRA, will reduce DC coupled market penetration?
I don't. To me, DC coupled is already so far in the fringe that I give it very little thought. But I think what Corey's getting at is there used to be a narrative that it was easier to prove ITC compliance for the combined solar storage ITC when you had DC coupling, because you can ensure pretty easily that an electron never came from the grid and went into the battery. That being said, it's really not that hard to prove prior legislation ITC compliance with an AC coupled system. If you have a meter at the POI, and if you have a meter on the solar farm, and if you have a meter at the battery, via some pretty easy arithmetic and if-then control logic, you can very easily ensure and prove to the IRS, if you ever got called into question, that you didn't charge from the grid. So from under prior legislation, during the 5-year ITC recapture period where you couldn't grid charge, I think whether it was DC coupled or AC coupled, didn't really matter. There was a way to get through that. So I may not be thinking through all the variables because there's a lot of pieces to the Inflation Reduction Act and a lot of unintended consequences, but I don't think it's going to change the balance that much.
Right. Any thoughts to add to that, Ivan?
No,
From your end?
I think you hit it on the head, Joel.
Got it. All right. A question from Surav. What energy storage chemistry is suitable at minus 30 degrees Celsius for microgrid applications?
Oh man, I lived in northern Canada for years. You're bringing back some PTSD. I don't know what you're solving for, but if you have a true robust microgrid, Where at -30, you're going to have to keep your reciprocating engine idling all the time because it might freeze up if you stop it. I would look at using engine jacket heat from your reciprocating engine and using that, free heat to keep a lithium-ion energy storage system warm. That would be my vote. But there's a lot of different permutations there, and when you get into some applications like that, sometimes lithium-ion is not the right solution. Because if you charge below, the freezing point, then you're at risk of forming dendrites, and it can be pretty nasty to try and get those systems unfrozen, especially at -30. But if you're running a 24/7 microgrid and your reciprocating engine's always running, I would take advantage of that engine jacket heat, use a liquid air cooled or a liquid heat exchanger, run through your battery enclosure to try and keep it warm.
And I know we didn't really touch upon too many different technologies outside of lithium ion, but it's fair to say that lithium ion is a family of different chemistries, some of which may actually work better at lower temperatures, some at higher temperatures, some a little bit more resilience to thermal runaway, and so on. Joel, or rather Ivan, are you seeing that the case?
So it's a good question. I don't focus on really severe cold weather environments. Our systems are designed to handle ambient temps as low as -30 Celsius and up to 50 degrees Celsius. So, beyond -30 Celsius, I mean, that's a pretty small portion of the market. So I don't spend my time, unfortunately, focused on that.
Well, it's Rob just said, it's a defense application at 18,000 feet, which sounds like an awesome project. But that 18,000 foot part, really adds an additional layer of complexity. Like I'd have to really think through it. Inverters don't like that altitude. HVAC doesn't like that altitude. Reciprocating engines don't like that altitude. So sounds like you have an awesome job, but I don't know what to tell you, man. But that's super interesting.
Yeah.
I've been told, I don't fully understand this, but I think some of the microgrid guys out there, like the Hitachis of the world and others, I think they've dabbled in federal government stuff. And when it's mission critical and cost doesn't matter, I think there's a lot of stuff you can do to solve this problem. But for a defense application, 18,000 feet elevation, I don't know what to tell you, but it sounds awesome.
Yeah, I can speak just a tad on that. I mean, I worked on a project in very high elevation as well. I think it was about 10,000 feet. And the problem you get into is that things don't derate at the same derate voltage at the same rate, and then they're not standard or tested to the same standards at that rate and that elevation. So I would just say it gets very complicated very fast and nearly impossible. Unless you don't need it listed, of course, and then you can basically assemble whatever you want.
Another question. Are you guys seeing deployment of energy storage, particularly more in standalone applications or coupled with DER resources like solar?
Depends where you're at. I think in areas where there's already a lot of solar, standalone storage made sense even before the passing of the Inflation Reduction Act. In other markets where there's not as much intermittent renewable energy yet, it makes sense to deploy them together. And sometimes it actually makes sense just to deploy a solar farm and not attach a battery to it. So it really just depends. I do think that the IRA changes the game on that, right? Like if the government's going to pay for 30% of your project, granted there's tax equity gets their cut and things that make it a little bit less than 30% by the time it goes to a developer, but that's going to open it up, and it should naturally incentivize more standalone storage versus co-location. It really just depends, though.
Yeah, I think you also have to consider congestion in that particular market and what the density of land is like in that, and availability of land is like in that area. We're working on a project like in Long Island, where it solves that kind of congestion issue, and obviously land is scarce there, right? So standalone storage makes sense.
Right. I just found this particular chart right here where, speaking further to what you guys said, the use cases, particularly coupling DER with solar together, really speaks very powerfully to that. So I think we are seeing more and more of that type of deployment to the combination of solar combined with storage. But to your point, it will work by itself. It will work coupled with solar. The two form a power team.
Yep.
when deployed together. Okay. As we come up to the top of the hour, this has been a really fascinating conversation. I think we could really talk for much longer. Each topic alone warrants a full hour, if not longer. Any final thoughts as we close up on this?
It's a great industry, and it's a great time to be in this industry. The last year, 2 years has been pretty tough and has had several unfun situations as the supply chain has blown up, and whether it's COVID or China stuff or Russo-Ukrainian war, just like force majeure event after force majeure event. It's been pretty unfun. But that being said, the Inflation Reduction Act is a pretty big game changer. I think the industry was standing on its own 2 feet even before that, and this is really just going to supercharge it. So, no matter what technology you're deploying in the space, or whether you're chasing microgrids, behind the meter, front of the meter, it doesn't really matter. I think it's a great time to be in the industry, and I'm pretty optimistic about it.
Yeah, I mean, just two thoughts. Number one, IRA, right? Can't say enough about the impact that's going to have on all of us in the industry. And secondly, I just think this transition from project-based engineering and execution, like Joel referenced, to more of a product execution and deployment is so exciting, because then you're starting to see nearshoring of production and a really fall in implementation and installation costs. And that's what's really going to keep the industry moving forward as we become the most economical solution for basically energy storage and deployment.
Thank you, Joel. Thank you, Ivan. This has been a really intriguing conversation, and I think we'll have plenty of opportunity to carry on, perhaps at RE Plus, SPI RE Plus in California, or at the AE World Expo, Energy Expo, happening in Atlanta the same week, in fact. So to the audience, if you guys have any further questions, please feel free to send them to us here at McKim & Creed, and we'll be sure that Joel and Ivan do receive them. Well, thank you all for really joining us in this stimulating conversation. And I also want to do a shout out to the multimedia and marketing team at McKim & Creed for putting all this together, as well to Parka, Addy, Kirsten, and the others for making this happen. So stay tuned on this channel, and we will be having further conversations, further panel discussions on energy storage and DER, probably after RE Plus. See you all at RE Plus. Thank you.
Take care.